minus 1 is equal to A transpose, that's the same thing. That means that the matrix is orthonormal, right? A matrix is unitary if it's orthonormal, but it's complex. So it's just simply the extension of orthonormality to a complex matrix. So a matrix is unitary if it's complex and orthonormal. An orthonormal. For example, the generic matrix A, B, e to the minus I phi times B conjugate, and e to the I phi A conjugate is unitary, where A and B are arbitrary complex numbers, complex or real, it doesn't really matter, right? And there is one constraint, which is that the norm of A squared plus the norm of B squared is equal to 1, but instead of me just saying it, let's just prove it, right? So if a matrix is unitary, that means that its conjugate transpose makes it orthogonal, right? Makes it the identity. So the way that I would multiply these two matrices is I write the matrix, now I'm going to transpose, so this is A and B, and then I have to use conjugation, right? So here is its Hermitian, and then this second row becomes the column, and in order to transpose, in order to conjugate, I have to take this to the I phi, and then this B conjugate becomes B. The asterisk means conjugation, and this becomes E to the minus I phi times A, right? So this is the matrix, and this is its conjugate transpose, or its Hermitian version. If we multiply these two matrices, then we get here, we get A times A conjugate plus B times B conjugate. And if we get here, we see that we get e to the minus I phi times e to the I phi is 1, and we get B conjugate times B. And then here we get e to the minus I phi times this is 1, and we get A times A conjugate. So this is again A times A conjugate plus B times B conjugate. And if we look what goes outside the diagonal, you will see that this is A times AB times e to the I phi minus AB e to the I phi. Whoops, wait, I got a wrong sign somewhere. My mistake. This is a minus here. So when I put this, I have to put a minus here, right? Apologies. So now we go A times minus this, B times this, so this is a 0, and then here A conjugate, B conjugate, A conjugate, B conjugate, this is a 0. So in order to make this matrix into an identity, then these two things have to be equal to 1, right? So A conjugate plus B conjugate must be equal to 1. That's the requirement, right? Now, remember from the multiplication of complex numbers that if we have a complex number A, its conjugate, it's this, right? And the multiplication of a number times its conjugate, which adds the faces, is always real and has a value which is equal to the product of the magnitudes, right? So in this case, we would say that this is the magnitude of A squared, right? So that's A times A conjugate. That means that this requirement simply means that the magnitude of A squared plus the magnitude of B squared is equal to 1. If we impose that constraint, then we have that this matrix, which I wrote here, for any A, any B, any phi, is actually unitary, right? Which again is the generalization of orthonormal for complex matrices. All right, moving on. Moving on in the jargon, we have the obvious upper and lower triangulars. Okay, that's kind of self-evident, right? It means that the diagonal and terms on top of the diagonal may not be zero, but all of this part here is zero, right? That would be an upper triangular, and lower triangular would be the opposite, right? Now, the next item is matrices called idempotent, which will show up sometimes, okay? So a matrix is idempotent when is a matrix idempotent? A matrix is idempotent if when you multiply it times itself, you get itself. Okay? That is, raising the matrix to a power does not change it. Now that is kind of weird at first, right? That means m to the k is m. Now that's kind of weird in the sense that for scalars, this would require that the m would be 1, right? Because the only thing that you can raise to a power and not change it is 1. 1 to whatever is 1. But in matrices, that's not true. You can have a matrix that has nothing to do with being a 1, which when you multiply it times itself, it gives it the thing back. Now, does that make sense? Well, yes, it is correct, but look at the following argument to confuse the issue for just a second. If it is true that this is true, that m times m is m, then if I multiply by the inverse of m, then I get m times the inverse of m is equal to m times the inverse of m, and that would give me that m times the inverse of m is the identity, and m times the inverse of m is the identity, and it would tell us that the only choice that we have for m is the identity. Now, it is true that m could be the identity, but it is not true that m is always the identity. So why is it not true that m is always the identity? Because the step that I took here in this derivation, which is not necessarily the case, is that I said multiplying by the inverse of m. What happens is that m, when this matrix is idempotent, is what we call rank deficient, which means it has no inverse. Okay? So m will always have, well, unless it's the identity, okay? Unless m is the identity, m is rank deficient. Now, rank deficient means that the matrix cannot be inverted, okay? Now, to look at one matrix that is an example of an idempotent matrix, for example, would be 2 minus 2 minus 4 minus 1, 3, 4, 1, minus 2, minus 3. For example, that matrix M is idempotent. When I was in the class yesterday, I actually typed it in MATLAB, multiply it times itself, and show that what you get is the same thing. If you're watching this video and you have your laptop in front of you, you might just want to do that. Okay, pause it for a second, type this M, multiply M times M, and you'll see that you'd get the same thing back. Now, it's obvious, right, that if M times M is the same thing, then M times M times M is the same thing, and it doesn't matter what power you use, you're going to have the same matrix all the time. So that's an idempotent matrix. Then, as I said, they are always rank deficient, which means that at least one of its eigenvalues is 0. Okay? So that's idempotent. The next one on the potent list is nilpotent. And nilpotent actually shows up even more than idempotent in identification in my personal experience. What we mean by nilpotent is that it is a matrix, okay, let's say Q, that when it's raised to some power, it is 0, even though Q is not 0, okay? Now again, that is something that you cannot have with scalars, because the only thing that it's equal to 0 when you raise it to a power is 0, right? But in a matrix, you can have a matrix and you raise it to a power and the matrix becomes entirely zeros. Now that's not what that power is depends to remains to be determined in this discussion. But let's say, for example, Q equals to 5 minus 3, 2, 15 minus 9, 6, 10 minus 6, 4 is a nilpotent matrix where K is equal to 2. That is, if you take this matrix and you multiply it times itself, everything vanishes. Okay? Once again, if you have a laptop right now or you're in front of your computer, type it in, multiply Q times Q, and you will see that it becomes 0. Now, nilpotent matrices, one thing that we will actually revisit later on when we talk about the Cayley-Hamilton theorem is the fact that the maximum power for which nilpotency can be reached is the order of the matrix. That is, if I have a 3 by 3, and when I put the power 3 is not 0, there is no point on searching for power 4 or 5 or 6 because it is not possible to make it 0. The matrix is not nilpotent. If I have a matrix and it's 10 by 10, if it is nilpotent, the power must be 10 or less. 10, 9, 8, 7, 6, etc. But it cannot be 11 or 12, right? Now, nilpotency means that it's extremely comes out all the time because certain algorithms can be manipulated so that some of the matrices that are involved in the algorithm become nilpotent. When that happens, that means that if there is a recursive procedure that requires multiplying that matrix times itself over and over, then that procedure actually at some point flat out finishes and you get the exact answer at that point, right? There is no more one more time because everything just went to 0, okay? In the jargon of system identification, we normally refer to those situations as having a deadbeat observer, but they're all connected with this nilpotency. It should also be noted briefly that all matrices that are upper or lower triangular, including the diagonal, are nilpotent. So for example, matrices of this type, let's say 0, 2, 1, 1, 6, 2, 3, for example, something like that, right? Which is upper triangular with the diagonal of 0, that will be nilpotent for sure. Now that matrix, you can try it, you will see that it is not nilpotent with K equal to 2, it is not nilpotent with K equal to 3, but it is nilpotent with K equal to 4, okay? All right, so that's Actually, I have two more matrices here, names which are Hankel and Toplitz, but I did not, for some reason, yesterday in the class mention them. I just kind of skipped them unintentionally, so I'll just skip them here too and talk about it in class tomorrow. Okay? What I did after this point was, having discussed a little bit these special names that often pop up, I know that this is a topic that you've all had probably more than once before, but it's worth bringing it back. We will talk about them, about eigenvalues and eigenvectors, you know, on and off repeatedly throughout the class. So it's good to introduce them from the beginning and just make sure that we're on the same boat. So if we have a matrix A, right, that matrix has to be square in order for us to talk about its eigenvalues or eigenvectors. Only square matrices have eigenvalues or eigenvectors, right? So if we have a matrix A and we find that when the matrix A is multiplied times some vector, what we get out is the same vector, perhaps scaled by a number, then we say that this number, which is a scalar, is an eigenvalue. And we say that this vector, which had that property, is an eigenvector. Now, let's say that I discussed here the case where A is an n by n matrix. Okay, so if A is an n by n matrix, then phi is a, doesn't need to be real. A could be real, but phi could be complex, n by 1, and lambda is complex 1. Right? One entry, so it's a scalar. So eigenvalues, eigenvectors. Now, a fundamental theorem tells us that if a square matrix is of dimension n by n, it will always have n eigenvalues, right? All n by n matrices have n eigenvalues. But we should make sure that we understand that that is counting repetitions. This idea of repetitions is not always well explained or clarified. So when we say that a matrix A has n eigenvalues including repetitions, what do we mean? Well, what we mean is this, and it's perhaps easier to show by recognizing that eigenvalues are roots, right, of the characteristic polynomial. So lambdas are the roots of the characteristic polynomial, and the characteristic polynomial is simply the polynomial of the determinant, the matrix times the identity minus s. Okay, so if you looked at the determinant of that, that determinant would be, you know, like s to the n plus a1 s to the n minus 1 plus a2, it's, well, actually I should say a0 here if I want, plus etc., etc., right? There is some polynomial which is the calculation of this thing, and the roots of this polynomial, that is the ones that make them equal to 0, the values of s that make them equal to 0 are the eigenvalues. So that means that if this here is s, this thing could be doing like this, right? Let's say like this. So in this case we would say that this, I mean, of course I'm showing it in the case of the real axis, they can be complex, but that would be delta 1, I mean lambda 1, this would be lambda 2, this would be lambda 3, right? And this is s. So what we are saying is that the values of lambda shown here in real, but they can be complex, right? Or usually are complex, as I will mention in a minute, but, or emphasize. But the point is that they are roots. What I'm trying to do here is just simply show graphically what is it that we mean, or what is it that it means when we say that an eigenvalue is repeated. You can see here that if I change the parameters of the matrix, it may be that the new set of eigenvalues could be this. And then you can see that now lambda 1 and lambda 2 are getting close. And here is lambda 3. Now in the limit, there may be a set of parameters for which this thing just goes like this, right? And it just touches here. And so that means that lambda 1 and lambda 2 just became equal, right? Now you could say, well, what do you mean they're equal? It's just 1. Well, okay, you can just say that if you like. But what it means is that in that case, this point in which there is this eigenvalue here is not only a point where the characteristic polynomial is 0, but the derivative of the characteristic polynomial is 0. Okay? So at this point, we have a 0 slope here and a repeated eigenvalue. All right? So repeated eigenvalues are, well, they are a thing that requires a lot of time to talk about to do it really well. Not the point to do it right now. But let's just, for the moment, stick to the simpler situation, which is almost always the prevailing one, where the eigenvalues are distinct. So we have a matrix A, which is real, and it's n by n, and we have n eigenvalues. Okay? We have n eigenvalues, they are different. Now, if the matrix A is real, then that means that the trace of A, right, is a real number. The trace of a matrix is just the sum of the diagonal, right? So if the trace of a matrix is real, if the matrix is real, its trace is real. And what that means is that because we know that the sum of the eigenvalues of a matrix is equal to the trace, then we know that the sum of the eigenvalues is real. Okay, so the point is that A is real, the eigenvalues may be complex, but if they are complex, they have to come in complex conjugate pairs, so that when they get added, the answer is real. Okay?